We finally get to talk about how you would design a gear set. And we'll start with our demotivational poster, which says welded gears fail. So you see these gears that are welded together. One would be called the pinion and the other one the gear. It says do not take everything you read on the internet literally. So I guess someone thought it would be a good idea to weld these two gears together, but of course the purpose of gears is to allow for relative motion. I'm sure this was done as a joke. Well, some of the stuff I've seen on the internet, this may not have been done as a joke. Someone may have thought this would actually fix their gear set, but obviously it would not. So we're going to begin, though, by talking about spur gear design. The gears we just saw were a very special type of gear. They're different than what we're talking about so far. Those were a hypoid set. But we're talking about just plain, simple gears. Let's start off with the concept of gear quality. Gears can vary quite a lot in their quality and how good they are and how good they're made. And there's many different types of imperfections that can be present in a gear. For example, index variation is really just the difference between where a particular point on a gear tooth should be and where it really is, at least at the pitch diameter. Tooth alignment, if you think about a spur gear, for example, how straight are the teeth with respect to the gear axis itself? So how square are the gear teeth to the gear face, for example? Tooth profile, that's how much the tooth varies from an ideal involute profile. It's no matter how carefully you make anything, it's going to be imperfect to some extent. And so tooth profile variation is just how perfect the gear is versus the shape it's supposed to be. Root radius, if the root is not cleared out enough, there can be interference. Of course, stress concentrations occur at the root. Run out is how out of round the gear is, so lack of roundness, and also eccentricity. How far off is the pitch circle of the teeth versus the center of the gear itself, the bore of the gear. Total composite variation is what we usually measure. Rather than looking into the details of all these various deviations, instead what we do is we just look at and measure the total composite variation. And so the idea here is if we make a gear very, very carefully, call it a master gear, and make it just as precise as we possibly can. These are expensive gears, but if we can make it, we could use it as a reference gear, something that we could run a gear we've just manufactured against, and see how much deflection there is of the master gear. Now, if you look at the figure, you'll understand what I'm saying. The master gear is on the left in cross-section. It's sort of a gold-yellow color, and is riding on a cart where that cart is spring-loaded to ride against the production gear as tightly as possible. And then there's a simple gauge on the left, a dial indicator, to show how far that cart moves back and forth as the two gears mesh together. And so this is the simplest way to measure gear quality, and it really captures all the different imperfections in a gear. And of course you have to have a master gear or a very precise gear to do this, but that can be manufactured, though they are expensive. There are various standards for gear quality, and here's a rough correlation between them. AGMA 2000 and AGMA 2015, these are the years that the American Gear Manufacturers Association released their new standards for gears. So 2015 is the update from 2000. It's about 15 years later, obviously. And they changed from a so-called Q system to an A system to be more closely aligned to the ISO standard. And so the International Standards Organization is, that standard number for gears is 1328, and AGMA either 2000 or 2015. Here's a rough correlation between them. A Q5, which is a low precision gear, is about equivalent to an A11 AGMA 2015 or a number 11 ISO gear, similar on the high precision side. So in the past, as the number went up, the precision of the gear went up. Now it's kind of opposite. It's backward of what you might think. And as the number for the quality of the gear goes up, the actual precision goes down. There is a DIN standard, which is German, and there are some recommendations on page 330 in your text. Now, as we go through this lecture and as we go through the example problems, it is critical that you have your book open and you're tabbing and marking important things. I've tried to include as much as I can remember in the slides, but here's certainly one. Page 330 definitely deserves a tab in your book. or at least a highlight where you know how to find it quickly, because it's the table that tells you what quality of gearing typically would be used in what application. I mean, how do you know what quality number you would use in a cement mixer? Obviously, it's going to be a lower quality gear than in a, I don't know, a motion control system for a precise robot or something. But how would you know? Well, this table gives you that answer. So make sure you know how to find that table. There are many different materials that gears can be made from. Plain carbon steel is probably the most common. It's economical. Cast iron is commonly used for very large gears or complicated gears. One item not on this list is sintered metal. So metal where you've shaped the gear. Just like cast iron, you can make fairly complicated shapes out of it, because powdered metal is the word I was looking for, because you can press the powder into a fairly complicated mold, sinter it, and then have a decent gear. Cast iron traditionally has been used for larger or more complicated gears because you're pouring the metal and can make fairly complicated shapes. There are also gears that are then heat treated or are made of alloy steel, and these are typically used where you need a very small gear and therefore expect very high loads, and also you need wear resistance. So this is one place that type. Now, this is not necessarily a different material as much as it is a different treatment, although an alloy steel is a very different material. But heat treatment can make a big difference in gears' properties as well. Bronze is commonly used for worm gears, whereas the worm itself is always made of steel. Plastic and aluminum can also be made to make gears, and these are in common use for relatively inexpensive, lightly loaded gears. I know when I was a kid, I fixed my mother's garage door opener, and as I wouldn't raise the door anymore, I took it apart, and sure enough, there was a plastic gear that was used right off the, how was it? Well, the motor had a worm, and the plastic gear was actually a worm gear, and the teeth were literally chewed off of the worm gear. It had just been used for so long. Turns out it was a common, easy to find replacement component. I think I probably gave a whole $15 for the new gear, put it in, and it worked fine. But for light duty, or where you've designed it carefully, plastic or aluminum can be used as a gear. Now, usually when we're running a gear set together, the pinion, of course, is smaller, and so it's usually made harder to minimize wear, because if you think about it, as the pinion rotates, the teeth on it see a lot more cycles and a lot more wear than the gear sees, simply because it's turning faster. So there are more engagements per revolution of the pinion, or per, how should I say this? Per rotation of the motor, let's say, whatever's driving it. There's more rotations or more loadings of each tooth on the pinion than on the gear, and so it's pretty common to make the pinion the beefier or stronger material. How do gears fail? Well, they can fail a couple of different ways. Teeth can break just due to bending stress. If a gear set is simply overloaded, the teeth can simply snap off. If you think about a gear tooth, it's kind of like a cantilevered beam. It's not a very long cantilevered beam, but it's still a cantilevered beam. So if you look at the lower right-hand figure, you'll see teeth that have literally been just simply broken off. The more common way that gears fail, if they're designed correctly, well, almost correctly, is by contact stress, so fatigue, where if you think about what's going on, when two teeth of gears mesh together, there's high forces between those teeth, and those are surface forces. Those are forces being transmitted between two surfaces. And the theoretical contact, in spur gears at least, is a line, which is zero area, and so theoretically you have infinite stress. What that means is that the gear teeth, the surface of the gear tooth, will literally deform some. And as it deforms, in order to have a non-zero area so that the stress is non-infinite, you still end up with very high stresses. And if you think about what happens once that tooth goes out of mesh, well, that stress is completely relieved, but when it comes back around, it's reapplied, and so on, and now we're in the world of fatigue failure. So contact stress, or surface pitting, is a very common problem for gear teeth, and you have to design against that as well. In fact, a lot of times you'll start off your design by designing against bending stress and come up with a gear design that should work, and then you go through the contact stress calculations, you find that you're not even close. You need a much beefier gear. But we'll see all that more in the context of example problems than lectures. There's a lot to it, and there's a lot of tables, a lot of figures, a lot of information you need, so make sure as you're watching the example problems you've got your book open, your highlighter, and your tabs handy, because you will definitely want to make some notes in your book. Another problem can be material or manufacturing imperfections. Gears are not made perfectly. Their geometry as well as the material that they're made from can be imperfect, and this can lead to failure. There can be extreme overloading, of course, where all of a sudden there's a huge load imparted to the gears and they just fail. If you have a gear that is lightly loaded, that's a small gear, you typically design it for tooth breakage. But in power transfer gears, which is what we usually are concerned with, then you would design for both the bending stress in the teeth but also for contact stress. And in that case, most of the time, these types of gears that are used for large numbers of cycles and continuously, think transmission gears in your car or in an airplane, these will usually fail from surface fatigue. Now, if you think about small, lightly loaded gears, why would we design those for tooth breakage? Well, a lot of times, small, lightly loaded gears, like the gear I explained in the garage door opener, these are not used for very high numbers of cycles. And so you don't expect cyclic failure. In fact, you simply expect it to possibly be overloaded and cause failure. Now, in the gear that I replaced, it looked like it had worn down over time, so probably the life of that garage door opener had been greatly exceeded from what it was designed to last, and simply that it had exhibited wear failure. But that was a different type of failure. That was not a fatigue failure because we were talking about plastic, and all that had happened really is the plastic had worn down over time. So I'm sure that the lifetime of that design was simply exceeded. That's all that happened. Now, some of the objectives you have when you're designing a gear set are that the set be compact, that it be quiet and operate smoothly. You want whatever life the equipment is supposed to last, that you would want it to last for that life. Not necessarily a super long life. Like I said, that garage door opener was probably designed to last 5 years, and I think she probably got 20 years out of it by the time it was all said and done. It needs to have a reasonable cost. It needs to be economical. And of course, what is low cost depends on the application. If you're talking about a cement mixer, the gears don't have to be all that precise. You expect there's going to be cement dust and all kinds of junk that get in between the teeth. And so you expect to not make very precise gears, and you expect them to be relatively low cost. Now, if you need extremely high precision gearing, for, say, moving a telescope in space or to view space, and you need very small, precise movements, you can expect a precision gear like that to cost a lot more. They need to be relatively easy to manufacture and, of course, compatible with shafts and bearings and all the sorts of things we would put, all the other machine elements, in a machine. Now, there is a gear design procedure you will want to mark. It's on page 348, and I will refer to it as I go through example problems. The power-torque-speed equation will come into play again, because understand that the goal of gears is to transmit power. Most of the time we don't design a gear set to say, I don't know, to imagine a gear set that's used for opening a door, okay, or for raising a load. Well, most of the time the purpose of a gear set is to transmit power from a prime mover to some machine. And while you could argue that the door in my example would be the machine, really a door that's raised and lowered, for example, just doesn't see that many cycles. And so that's not really what we're talking about when we're talking about power transfer. Think more gearing in a drive system like in your car, for example, for a not commercial, but a consumer example. The force on the gear teeth is what will certainly cause failure in the teeth, and so we have to somehow calculate it. The piece that we really want is the tangential load. The tangential load is the horizontal component, you can see it there in the figure, that actually causes a moment, a torque, about the gear and causes the gear to rotate, transmitting power. And so that's the particular load that we're interested in. Of course, it's related to the torque on the gear through the radius of the gear, or the diameter over 2. And you can see that the first two equations are the same thing, just rearranged. They're in your text as well. You may want to highlight them. We'll use them over and over. The radial load is a side effect of the fact that we have to use teeth that are involute shaped. It's a trade-off. It's something we have to give up. We wish we didn't have the radial load, because what the radial load does is it tends to take the two gears, the gear and the pinion, and push the teeth apart from one another, trying to push them out of mesh. And of course, the higher the tangential load, the higher the radial load, and the more the teeth tend to be pushed apart. Now you might wonder, how do we get this radial and tangential load? Well, remember, we're going to put oil on the gear teeth so that there can be no force tangent to the face. All the force has to be normal to the face. So the actual load between the teeth is the normal load, W sub n. Now, you notice we're calculating the normal load from the tangential load based on the pressure angle. This is intentional. Even though the normal load is the actual load applied, the load we're interested in is the tangential load. So everything is based on the tangential load. All right, so finally, if that's the loading on the gear teeth, how would we analyze the stress in the spur gear teeth? Well, there's the so-called Lewis equation, and I'm sorry it's a little small on the screen. I guess I need to increase the size of that equation. It's in your text as well. But basically, all this does is begin by treating the tooth as a cantilevered beam. Now, there's a little more to it than that because it's not a typical cantilevered beam, and so you might see that the stress is listed there as a normal stress, and that's expected because in a beam, what causes failure is the normal stress due to the moment, right? So the bending stress. And you see the tangential load, which makes sense, and then you see the diametral pitch, which has to do with the size of the gear tooth, the face width, obviously the wider the beam, the more load it can take, and then what's called the Lewis form factor. The Lewis form factor takes into account the fact that the beam is not the typical beam you would deal with. It also takes care of the diametral pitch to make this equation true. Now, one thing about this equation, it does not take into account the stress concentration at the fillet or the root of the tooth. Now, if we were to include stress concentration with a stress concentration factor K sub t, then you'll notice K sub t and y would just be functions of the geometry of the gear, and so we could put those two together and call it a geometry factor J. And here's the Lewis equation updated with a geometry factor J. However, there's so many other factors that affect the life of a gear and the strength of the gear and so forth that the Lewis equation is actually not used. What's used instead is something called the bending stress number, S sub t. So you notice we've dropped the sigma, which would strictly indicate a stress, and now we're using S. Now it's called a bending stress number because it doesn't necessarily estimate the actual stress in the gear tooth, but it's the effective stress due to everything else. So you'll notice the first ratio there, that first fraction, Wt p sub d over Fj, is just the Lewis equation. But the rest of these factors are factors that more closely incorporate other things that can cause damage to the gear teeth. And we'll go through each of these. You notice there are 5 K factors, and we'll go through each one. KO, and again I'm sorry that this is small, KO is called the overload factor, and basically this takes into account any vibration, shock loading, load variations that can happen. If you think about it, when you put your car in gear, if you have a manual and you step on the gas, that's a lot more load on the transmission and the gears in the transmission than when you're just cruising down the road. What if you try to spin your tires, right? What if you try to hit the gas, pop the clutch, and get your tires to brake and spin? Well, that's going to be a very high shock load. So those sorts of things are what are taken into account with the overload factor. Of course, in industry, you're not popping the clutch. Instead, what we're talking about there are things like engines that have higher torque spikes as the pistons come around, or machines like rock crushers that can choke, or that have very high sudden impact variations in loading. The size factor, K sub s, and notice I've referenced page 337. You should be on that page now, and you'll want to mark this page as well in your book because you will reference these factors all the time. But the size factor has to do with the size of the teeth. So if you have a larger face width, then the size factor comes into play, because the larger the face width, if you think about it, because of manufacturing variations, it's less likely with a larger face of width of the teeth, it's less likely that the full face will be used equally. In other words, the face is going to be imperfect, and those imperfections means there will be hills and valleys, if you will, where the hills are making contact and the valleys aren't. And so there's going to be higher stress in the teeth due to imperfections in the teeth, and the larger the tooth, the more likely there to be more and larger imperfections. Km is called the load distribution factor. It's on page 338. In the standard, the AGMA standard, it's actually a very complicated calculation. We're going to simplify it just to simulate it for the sake of our course. It consists of a pinion proportion factor and a mesh alignment factor. I hope I got those two right. I always confuse those two, but you'll see me use those in the context of example problems, and you'll see me confuse the wording, so I hope that doesn't confuse you too much. But I'll explain more about those two and how to use them in the context of example problems. The rim factor is another factor that's important, and if you think about a large gear, you probably don't want to make a large gear with a solid hub going all the way out to the rim itself. You'd probably want to use spokes. But if you use spokes, then you're going to have a fairly thin rim that the teeth ride upon. And as the teeth go in mesh with other teeth, the forces are going to cause deflections of those teeth and can possibly cause deflection of the rim itself. If the rim moves, well, that's going to affect the tooth stress, and that's what this rim factor takes into account. You'll notice that after a certain ratio between rim thickness and tooth depth, that the factor is just 1. In other words, the rim is pretty much rigid and has no effect. And I think that's, if I remember right, it's about 120% of the tooth height. So once the rim is thicker than 120% of the tooth height, you pretty much neglect the rim. Again, I'm sorry for the small size, but KV is the dynamic factor, and it's the effects of impact. So if you think about the teeth as they come around and come into mesh, there's some clanking that's going to occur, right? The gears are not perfect, and so the teeth are not perfect, so there's not necessarily going to be a perfectly smooth transition of engagement from one tooth to the next. And that dynamic factor has a lot to do with the quality of the gears and the speed at which the gears are run. I mean, which is easier, to take a hammer and a nail and tap the nail in, or just whack the nail? Well, if you whack the nail, it moves in a lot faster. There's a lot more effect there. And so if the gears are moving at much higher velocity, then there's going to be much more effect, just like a hammer hitting a nail faster, right? There's going to be much more effect there. So the effects of impact and the quality are taken into account here. Again, this would be a page that you will want to mark in your book. It's page 341 if you can't read the slide. I apologize for the size again. I thought I had all this fixed. I'll try to fix it and upload the slides for you before you see this video. Anyway, so SAT, on the other hand, is the allowable tooth stress. Now, be careful. The bending stress number, S sub t, is our estimate for the effective stress in the teeth. Not really the stress, but the effect of all the other factors on the stress. And it's kind of like overrating the stress due to all of the velocity factors, the overloading, and so forth that are extra abuse to the teeth, even though the teeth aren't really stressed at a higher level. That's focusing on the load side of the equation. On the other side, what we want to compare to is the material strength. This is called allowable strength of the material. Now, we can't just compare this to, say, the yield strength of the material we make the gear from, or the ultimate strength. It's a little more complicated than that. Now, notice that the numbers we're going to use are typically for temperatures less than 250 degrees, 10 million cycles, and 99% reliability with a safety factor of 1. Now, SAT prime takes some other things into account. So, for example, if you think about the number of cycles that a gear has to undergo, well, that's going to be a fatigue type load. Notice we didn't put fatiguing on the load side, we're putting it on the material side. That's what Y sub N stands for. It's a fatigue type factor. SF is a safety factor, and KR is a reliability factor. What if 99% reliability is not good enough? Well, then we have to adjust it. And so SAT prime is called the adjusted allowable tooth stress. So what you do is you would calculate the bending stress number, S sub T, come up, if you choose a material, come up with the, let's go back to that, the adjusted allowable tooth stress, and compare the two together. And if the bending stress number is less than the adjusted allowable tooth stress, then things are fine. Now, to come up with the stress cycle factor, or what basically takes into account fatigue loading, we have to first of all calculate the number of cycles that we expect for a gear tooth to undergo. And so L in this equation is the design life in hours. So, for example, a car is not made to last all that long. You may want to look up in your book and see the recommended design life for an automobile. You may be surprised because you know that you can probably buy a car, and if it's a decent car, it'll last you 20, 30 years if you really take care of it, right? So you might be surprised to see that cars are only made to last in the thousands of hours. And you might say, well, that doesn't make sense. There's a lot more than 1,000 hours in a year. Yes, but you don't drive your car most of the year. This is why taxis actually look so bedraggled after a short period of time, because they're not designed typically to last for as much time as they're being driven. When a taxi is being driven, 16 hours a day, its life goes away very quickly because it's simply not designed to last that long. This might give you an idea as to why selling your car essentially to Uber and whatever the other ride services may not be the best idea. But that's up to you. That's a calculation up to you. So anyway, the number of cycles then that a gear tooth will see is given here. The 60 is just a conversion factor. L is the life in hours. N is the speed of rotation, just assuming a constant speed. And Q is the number of loads. Now, the Q may be a little bit confusing at first, but it's actually very simple. If you think about two gears simply in mesh with one another transmitting power, every time a tooth comes around into mesh, it's loaded once. But what if you have two gears and you want them to rotate in the same direction? Well, as we said in the kinematics section, you could simply insert an idler gear. Well, that's all well and good, but the idler gear has to mesh with both gears, and as one tooth goes around, it meshes with gear A and then also with the output gear, gear B. And so the tooth sees two loading cycles per revolution rather than one. And so Q is a type of gear factor, and if it's an idler, then it's set to 2. If you think about it, if you had 3 gears around a single gear like you would in a sun gear, then you've got 3 loading, and Q would actually be 3 loads per rotation. The reliability factor, there's a table 911 on page 344, another page you need to mark, and then the safety factor is just there for any other uncertainties you might have in analysis. Now notice we've tried to be pretty careful here on the material side and the load side, and so usually the safety factors, you don't usually see a safety factor for gearing that's 10, Usually the safety factor is between 1, 1.5, because we take so many things into account.